Right, this is the next video for the year to pure, what we're going towards, 11D. And before we go straight into the example, I just want to think about, this differentiation. If I want to differentiate the log of x squared, for example, I'd use the chain rule, differentiate the whole thing, so 1 over x squared, then multiply by the derivative of the bracket. And of course I could simplify that 2 over x, but I'm not going to. Let's try something else. Let's try the derivative of the log of 3x plus 2. Well, 1 over 3x plus 2 multiplied by the derivative of the bracket. And I'm sure you can see, using the chain rule, the derivative of the log of a function equals that function with its derivative on top of the fraction. So the log of a function is 1 over that function times by its derivative. So in general, the derivative of the log of some function of x with respect to x is 1 over that function multiplied by the derivative of that, or f dash x over f of x. So that means that if I've got an integration that looks like this, then I can integrate to get the log of a function. So if I've got a function written like f dash x over x, then I'm going to attempt to differentiate log f of x and see if I need to fix it with a constant. So that's what this is all about, the reverse chain rule. Example 8, 2x over x squared plus 1 dx. Well, I recognise that the numerator is the derivative of the denominator. And I've spotted that because I've done a billion of these. So I'm going to attempt to differentiate the log of x squared plus 1. Well, that's going to give me 1 over x squared plus 1 multiplied by the derivative of my function, which is 2x. So that is 2x over x squared plus 1. So the integral of this must be log x squared plus 1 plus c. Again, another example of, I've done the integration by differentiating, by being intelligent and guessing, I suppose, what differentiates to give this, but it's recognising that the numerator is the derivative of the denominator. And b is the same thing. I'll just have to fix the constant. So the integral of cos x over 3 plus 2 sine x. Well, again, I recognise that the numerator is the derivative of the denominator, because sine x differentiates to cos x. You know, give or take a constant, we can fix things by multiplying by constants. So I'm going to attempt to differentiate the log of 3 plus 2 sine x. Well, that equals 1 over 3 plus 2 sine x multiplied by the derivative of the bracket, which is 2 cos x. So 2 cos x over 3 plus 2 sine x, and of course that's twice as big as I want it to be. So it's a half log 3 plus 2 sine x plus c. So if I get something that looks like a constant times by a function as a denominator and its derivative as the numerator, try to differentiate the log of f of x and then adjust if I need to multiply with a constant. Now, there's a similar method. Let's try, if I differentiate 3 plus 2x to the 5. Because that chain rule says 5 times 3 plus 2x to the 4 multiplied by the derivative of the bracket. So 10x 3 plus 2x to the 4. Now what I'm noticing is this here, the 10x, give or take a constant, is the derivative of what's in the bracket. And of course that's going to work with anything that is a function of a function. Differentiate the whole thing. 7 times 2 plus 3 sine x to the 6 multiplied by the derivative of the bracket, which will just be 3 cos x. So that's going to be 21 cos x 2 plus 3 sine x to the 6. Now again, I'll notice, ignore the constant because it doesn't really matter, we can multiply by a constant to fix things, but cos x is the derivative of the bracket. So in general, to integrate a constant multiplied by the derivative of a function multiplied by the function to some power, we can try to differentiate the function to the power plus 1 and then fix with a constant. And that's what example 9 is. Example 9, integrate 3 cos x sine squared x. Well, of course, cos x is the derivative of sine squared x, because remember that means sine x all squared. So I'm going to differentiate sine cubed x. That gives me 3 sine squared x multiplied by the derivative of sine x, cos x, 3 cos x sine squared x, which is what I want. So the integral, again I've done it by using the chain rule to differentiate, sine cubed x plus c. And I think this is one of the most difficult methods because you need to spot, I've got a product of two things and one is the derivative of the other. Let's do the rest of example 9, part B. The integral of x squared plus 5 cubed dx. So again, I've noticed that x is the derivative of the function in the brackets. Well, it's a, give or take a constant. So I'm going to attempt to differentiate x squared plus 5 to the 4, and that's 4 lots of x squared plus 5 cubed multiplied by 2x. So 8x x squared plus 5 cubed, which is 8 times as big, but I can easily fix that with a constant. So the integral of this expression must be an 8th x squared plus 5 to the 4. Now once I've got the hang of this, this is a lot more efficient than expanding this expression out. And marks and time allotted in the exam would reflect that you'd be expected to use this strategy. Okay, example 10. Cosec squared x over 2 plus cot x cubed dx. Now, if that 3 weren't there, I could try log of 2 plus cot x. That means this is, that not being a single power on the bottom, that means this is not a log question. Again, I know that cot differentiates to cosec squared, while I'm talking to you. I'm just looking on my screen to check that out. Yep, cot differentiates to minus cosec squared. So I'm going to rewrite this integration as cosec squared x times by 2 plus cot x to the minus 3. And that's easier to see, I think, that it's the same as this last example. Cosec squared, give or take a constant, is the derivative of my bracket. So I'm going to differentiate 2 plus cot x to the minus 2. That'll give me minus 2 plus cot x to the minus 3, multiplied by the derivative of the bracket, which is minus cosec squared x. So it's 2 cosec squared x, 2 plus cot x to the minus 3, which is, give or take, what I want. I'll just fix it by dividing by 2. So a half of 2 plus cot x to the minus 2 plus c. And the last one, I'm given some limits. Example 11, 0 to theta 5 tan x sec to the 4x dx is 15 over 4. Theta is between pi by 2 and 0, and I need to find theta. Find theta. Let's start a new page. 0 to theta 5 tan x sec to the 4x dx. Now, sec, let's just have a think about this. I'm just going to pause it. I had to think about this, which is why I've just paused it. This is not a nice one, and the reason this is not a nice one is because the derivative of sec x is sec tan. Sec x tan x. So I'm going to rewrite this as 5 lots of sec x tan x. That's my derivative times by sec cubed x. So I can see that sec tan is the derivative of sec. So I'm going to attempt to differentiate sec to the 4x, and that gives me 4 sec cubed x multiplied by the derivative of sec x, which is sec x tan x. 4 sec to the 4x tan x. Now I'm after 5 sec to the 4x tan x. Well, I'll just divide by 4 and times by 5. Or divide by 4 times by 5 sec to the 4x between theta and 0. That wants a bit of thinking about. So 5 over 4 sec to the 4 of theta minus 5 over 4 sec to the 4 of 0. Sec is 1 over cos. Cos of 0 is 1. So sec of 0 is 1. 5 over 4 times 1 is 5 over 4. So 5 over 4 sec to the 4 theta minus 5 over 4. And of course that equals, what does it equal? It equals 15 over 4. So I can divide both sides by 5, multiply both sides by 4, sec to the 4 theta minus 1 equals 3. So sec to the 4 theta equals 4, which means cos to the 4 theta is a quarter So cos theta is the fourth root of a quarter. Well, the square root is a half. So the fourth root is 1 over root 2. And of course it's plus and minus 1 over root 2. Now theta is between, where did I write it? 0 and pi by 2. So here's my cos graph. Pi by 2 there. So cos theta must be positive 1 over root 2. So cos theta is 1 over root 2, and my calculator will tell me that theta is pi by 4 radians. So not a nice one, and a good example of having to spot that this is a derivative times my original function, and yeah, I had to think about that one. Okay, see how you get on with 11D. Bye bye.